let's talk about one of the most elegant, most perfect relationships in all of geometry. And it all starts with a really simple idea. What happens when a perfectly straight line and a perfect circle meet on a flat plane?
It sounds almost too simple, right? But it turns out there are only three possibilities. Just three ways this little interaction can play out. So let's dive in and break them down one by one.
Okay, first up, the most obvious one. The line and the circle could just miss each other completely. They have absolutely 0 points in common. We call this a non-intersecting line. Easy enough, right?
Now for possibility number 2, the line could slice right through the circle, kind of like a pizza cutter. It crosses it at two separate, distinct points. This guy has a name. It's called a secant.
And then there's the third option, the one that's the most interesting. The line doesn't miss and it doesn't cut through. Instead, it just grazes the edge, a perfect glancing touch at exactly 1 point, and then it just keeps on going. This very special line is what we call a tangent.
So yeah, this whole single touch thing, it's the crucial idea here. It isn't just another option, it's actually a doorway to some incredibly cool and powerful rules in geometry. Let's really take a closer look at how you even get a tangent in the first place.
What's so wild is that a tangent is really just a secant in disguise, a very, very special case. I want you to imagine that secant line, the one that cuts through at 2 points. Now imagine it sliding. As it moves, those 2 points where it crosses the circle get closer and closer and closer, until, for one split second, they merge into a single point. And boom! Just like that, your secant has become a tangent.
Okay, so let's get the official definition on the books. A tangent is a line that intersects a circle at, say it with me, exactly 1 point. And the name itself is a dead giveaway. It comes from the Latin word tangere, which means to touch. It's literally the geometry of a perfect touch. How cool is that?
And that single shared spot, that exact place where they meet, it has its own special name too. We call it the point of contact. This is ground zero. It's the key to unlocking all the secrets of the tangent.
All right, now this is where the magic really starts. Let's say we draw a line from the very center of the circle out to that point of contact. That's the radius, of course. So what's the deal with that radius and the tangent line? How are they related?
So, have a look at this diagram. We've got our circle with its center O. We've got our tangent line just kissing the edge at point P. And we've drawn in that radius, connecting the center to the point of contact. What angle do you think they make right there?
Yep, exactly. They form a perfect 90-degree angle, a right angle. Not sometimes, not most of the time, every single time, no exceptions.
This is a big one. It's a fundamental rule of circle geometry, officially known as Theorem 10.1. The bottom line is, the tangent and the radius at the point of contact are always perpendicular. It's non-negotiable.
But why? Well, think about it for a second. That point of contact is the closest that tangent line ever gets to the center of the circle, right? Any other point on that line is going to be farther away. And in geometry, what's the shortest distance from a point to a line? It's always the perpendicular line. So it just has to be 90 degrees. It makes perfect sense.
All right, so we've got our first major rule locked down. Now let's switch things up. Let's change our point of view. Instead of starting with a line, let's start with a single point. How many tangents can we draw to a circle from that one point? Well, as it turns out, the answer completely depends on where that point is. Case 1. What if your point is inside the circle? Well, try drawing a line through it. Go on, try any direction you want. No matter what, that line has to come out the other side, right? It's always going to cut the circle in 2 places, making it a secant. So, from inside the circle, you can draw 0 tangents, none. Okay, case 2. What if your point is sitting right on the edge of the circle? Hey, wait a minute, we've already seen this one. This is our point of contact. And at any given point on a circle, there is one and only one possible tangent line you can draw.
And that brings us to case 3. What if the point is floating around outside the circle? Well, from any external point, you can always draw exactly 2 tangents to the circle. It creates this really beautiful symmetrical shape.
So, this beautiful symmetry brings us to our next big question. We've got these 2 tangent lines, and they both come from the same starting point outside the circle. What can we say about their lengths? Is there some kind of relationship there?
Now, just to be super precise, when we talk about the length of the tangent, what we actually mean is the distance from that outside point P to the point of contact on the circle. So what we're really doing is comparing the length of segment PT1 to the length of segment PT2.
So what do you think? What's the verdict? Is one longer than the other? Are they different every time? Or is there something more elegant going on here?
And here's the second incredible rule, Theorem 10.2. Their lengths are always equal. The distance from that external point to the first point of contact is exactly the same as the distance to the second one. It's just perfect symmetry in action.
So, let's do a quick recap. We've just added 3 incredibly powerful tools to our geometry toolkit. Number 1, a tangent touches a circle at just one point. Number 2, it's always at a perfect 90-degree angle to the radius right at that spot. And number 3, if you draw 2 tangents from any point outside the circle, they're always going to be equal in length.
And that really gets you thinking, doesn't it? We've just peeled back the curtain on these simple, elegant, and totally predictable rules that control how a line and a circle can touch. It just makes you wonder, what other perfect symmetries and hidden rules are just waiting out there to be discovered? Not just in a math book, but in the world all around us.